This is going to be just brief. All right, so vapor pressure of solutions. When you form a solution, the vapor pressure lowers. And so it's called Raoult's law. There's some diagrams of Raoult's law. Some more. This is interesting because this is the whole process of distillation, which we'll look at here. And so if you have a mixture of two liquids, you know, the higher boiling, the more volatile liquid, the liquid with the higher vapor pressure will come off first. And so if we have a mixture of like ethanol and water, we could try to distill off the ethanol to come up with pure ethanol over here and leave the water behind over here. And so that's the whole concept of distillation. It's taking advantage of the difference in vapor pressure. But the problem with alcohols is they form something called an azeotrope. An azeotrope is the maximum purity, let's say, of propanol you can get from distillation is only around 75%. Because of these curves here. For ethanol, do you know you can't get pure ethanol over there? You know what the maximum purity of ethanol you can get by distillation is? 95% ethanol. 95%. And so this from the azeotrope, not ideal. But vapor pressure also has an impact on certain things. Like solution A and solution B, if there's a difference in vapor pressure, do you know what's going to happen? If there's a difference in vapor pressure, yeah, try to equal that. And so there are two different ways of visualizing that occurring. One way is when we have solute particles there, let's say here, what we're going to do is we're going to have some kind of membrane in here, shown here, and separate a salt solution from pure water. Which one are we going to have more migration of? Water molecules this way. Let's say only water molecules can pass. These solute particles are too big. And so this membrane is called a semi-permeable membrane. Which one are we going to have more migration? Water molecules going up or water molecules going down?
Going up.
Going up, right? Going up.
That's elsewhere. That's
Right, right. And so, yeah, this has the this is the whole idea behind osmotic pressure.
Yeah.
There's another way we can visualize osmotic pressure. The other way we can visualize osmotic pressure is just strictly with vapor pressure. And so if we have a semi-permeable membrane here, and then on one side we put a, let's say, water here. On the other side we have some kind of salt solution. So what's going to happen now if we have salt mixed in with the water?
Are they separated?
Yeah, they're separated by a semi-permeable membrane.
Oh.
So these are salt ions in the water. This semi-permeable membrane only allows water to go back and forth, but not the ions, not the solute.
It's because it's sizer.
Right. And so, one way, we can visualize it like this, but the other way of visualizing it is like this. The water is going to exert a vapor pressure. Water molecules are going to vaporize off, and we call this the vapor pressure of pure water. Right? Over here, if we have ions in here, are we going to get as much vaporization off the surface?
Nope.
No, we're going to get less vaporization off the surface. And so this is the vapor pressure of the solution. Do you see they're mismatched here? And since they're mismatched, what's going to happen? Well, water is exerting a higher vapor pressure, therefore, yeah. What's going to happen is the two pressures are going to try to equalize. So we got this pressure, let's say, and we got this pressure here. And so what's going to happen is this is going to push down until the we get a scenario like this where the vapor pressure here plus the liquid pressure would just be, the height of this. So the vapor pressure plus the liquid pressure, let me rewrite that so it's easier to see, will equal the vapor pressure over here of the pure water. And so we want this to equal this. And that's going to cause osmosis to occur. That is, water is going to be forced through the membrane to the right side here, so the pressure is equal. Now, osmotic pressure, so what's happening here is the water is trying to force its way over to this side because the vapor pressure is lower over here, right? And the vapor pressure is higher over here. Oops, I forgot to turn the camera. And so what's trying to happen is water is being forced this way. To prevent the water from migrating this way because of the lower vapor pressure, we have to add some pressure here, add some weights. The pressure that we have to add is called the osmotic pressure. And so these weights equal the osmotic pressure required to prevent osmosis from occurring. Now, the higher the concentration here, the lower the vapor pressure. The lower the vapor pressure, the more weights we have to add here. And therefore, the greater the osmotic pressure. This is called reverse osmosis. If we add more than the osmotic pressure, what can we do? We can force the water molecules to go from the salt water side to the pure water side. And so this is a pressure greater than the osmotic. Osmotic is just the amount of pressure required to stop. What he's doing is he has a pump and he's pumping. And so he's putting greater pressure here and forcing it to purify the water. So reverse osmosis. Well, this is what happens to blood cells. Blood cells have a certain osmotic pressure given by the concentration of 0.9 grams of hypotonic saline. And so if you put blood cells in a hypertonic solution, hyper means lower, or no, hyper means greater. Excuse me. And something greater, concentration, what's going to happen is the blood cells are going to shrivel up, shrink, pickle. In isotonic saline, normal. In hypotonic, blood is going to absorb water, blow up like a balloon, and burst, right, rupture. So osmotic pressure is one of the things when vapor pressure is lowered. Colligative means a collection of properties. And the collection of properties is osmotic pressure, freezing point depression, and boiling point elevation all depend on the same thing, vapor pressure lowering. And so what happens when you lower the vapor pressure? This curve drops. So this is the pure liquid. You add solute, the vapor pressure drops. When the vapor pressure drops, what happens is the boiling point changes. Originally the boiling point was here, new boiling point's here. And the freezing point changes, the melting point. The melting point originally was here at the blue, but now it's here because the whole vapor pressure curve dropped. So these are colligative properties. Osmotic pressure, the greater the concentration, the higher the osmotic pressure. Boiling point elevation, the greater the concentration, the higher the boiling point. And freezing point depression, the greater the concentration, the lower the freezing point. We aren't doing any calculations. You can do the calculations using molalities. But here's some applications. De-icing or ice. And then the last part, actually the last two parts, one deals with ideal solutions versus non-ideal solutions. What do you think could cause a solution to deviate from ideal behavior? Concentrations, interionic attractions, like dimerization. that causes solutions to deviate. And so this is just showing, as the concentrations go up, the ions begin to attract each other. And so the expected concentration is different. And so if you have sodium chloride, that's two solute particles here, sodium ions and chloride ions. So we expect two solute. But what happens is, as the concentration increases, the solute particles don't completely separate. And so at 1.0 molal, 10% of the sodiums and chlorides are,
Gonna stay together.
yeah, they're attract. In other words, they form a pair, what's called an ion pair.
So they don't dissolve completely.
And they dissolve completely. They just stay together as a pair, like the dimer. They don't separate like they should. Sodium should separate from the chloride completely, but they're kind of stuck.
That's in the concentration.
Yeah, and the higher the concentration, the less ideal the solution becomes. The lower the concentration, the more ideal it becomes. The higher the charge, are we going to deviate more or less from ideal behavior? Higher charged ions deviate more or less from ideal behavior? More, because the ion attractions are
Great.
greater, right? And so there's some theories about this. You could do some corrections, which we aren't doing. It's not difficult.
What's that?
This is a colloid. This is a solution, this is a colloid. Colloid has solute particles that are big enough to scatter light, but they don't settle. And so milk is a colloid, and it depends on the particle size. This is a colloid. This is a precipitate, because eventually these crystals will settle. But the crystals here are too small to settle. You have to coagulate them. You know how to coagulate?
Heat it up.
Heat them up. Yeah. Like barium sulfate.
Tastes like the
All right. Let's go back to lab for today. We're going to build a couple of models.
You just build it and we can check it. Check it out. Can check it out.
He said we're gonna do two simultaneously. We're gonna do simultaneously.
All right. This is an example of a crystal lattice. And the thing with crystal lattices is they're very well ordered. So it's like a brick. And this brick makes up the whole lattice. This repeating brick is called the unit cell. And so we can build up the entire crystal by just repeating the unit cell. When we look at crystals, they have it all figured out. They have 7 different crystal systems depending on the shape of the unit cell. For example, if the unit cell is a cube, that's cubic. If the shape is a rhombohedral, it's rhombohedral. And so it goes from different levels. So there are only 2 shapes that we're going to be interested in: the cubic unit cell and the hexagonal unit cell. Hexagonal has a different angle in the unit cell. In the cubic unit cell, there are only 3 crystals, ways of packing the atoms into a cube. 3 basic ways, I should say, shown here. And so we're going to look at these in the cubic unit cell. Altogether, there are 14 different lattices, ways of packing in. You don't have to remember the numbers. And so this one is called simple cubic. Well, one thing is, this isn't the most efficient way to pack atoms, because do you see this huge gap in here? That's called the cubic hole. A cubic hole because it's got 8 atoms surrounding it. And so it's a fairly big hole. So let's go ahead and build this one. So build the simple cubic, just one of them. That's all we need.
How do we